guess Joel gave a nice overview of sort of the problem. I'll take a little bit of a different perspective. So yeah, this is a joint work with Kush and Jacob at UC Berkeley. But to give some more motivation, I think from sort of, it's, I guess, known that reward hacking is an issue, but there's sort of another like sort of growing trend in models in general is that they're becoming better and better at optimizing their objectives. So on the left is a picture from GPT-3. You can see as like the parameters get larger, the model does better on its objective. And then there's like clear economic incentives to create these models. You can see it's getting larger and larger, even though it's really expensive to train. Companies want these for their use cases. So this is a clear trend that will probably continue in the future. So this is good if we know what the objective is. Sort of, this is what Joel was talking about in general, is that at least for natural language generation, the objective is pretty clear. We just want to predict what the next word is. And it's good that we can do really well with this as we scale. But oftentimes, in like other scenarios that we care about, the objective isn't really precise. And so these are the three environments that we cover in our work: traffic control, blood glucose monitoring, and COVID/pandemic simulation. I'm not going to go into all of them, but you can look at our paper for more details. But in general, as sort of motivation, consider like the COVID simulation. If you're like a small business owner, you might care about lowering social distancing regulations because you want more economic growth. Whereas if you're like a hospital worker, you might care more about increasing social distancing regulations so that less people get sick and die. And we're not really arguing about like the morality or ethics of what is the correct policy. It's more just to showcase that people in general have different preferences. Stakeholders have different preferences. Oftentimes the reward isn't dense. It's hard to optimize for that. Or humans are just inconsistent with what they want. And it's sort of like specifying these rewards is hard. And so when we actually try to optimize for these imprecise objectives, it's not so clear that we're doing quote unquote the right thing. And so I sort of use the exact same example as him, but yes, this boat racing thing is quite nice. I think it's a very classical example in prior literature of like, basically, so what the, if you can play the video, what the designers were trying to do was make the boat go as fast as possible along the track, and then so they thought it would be a good idea to add these like green boosts, but then the boat just like picks up all the boosts instead of actually going around the race. And there's, as Joel showed, there's a lot of these examples in the work. And so more concretely, sort of what's going on here is that we have this like intended true objective. This is usually, like, as I mentioned, hard to specify. And for numerous reasons. We sort of break this taxonomy down in our paper, but there's like sort of different ways this could arise, and as a result, people don't want to actually optimize for the true objective. If they could, they would just do that, but instead they write down this proxy. And so now there's like this misspecification, because you're optimizing for this proxy, but you actually want to evaluate on this true reward, and then you get reward hacking. And basically, our perspective is that reward hacking occurs when the misspecified proxy gets over-optimized. So there's this notion of becoming too good at what you're doing. And so I think you need to click next, because otherwise the video will keep playing. Thanks. Yeah, so this is what I'm going to briefly go into in this talk, mostly sort of outlining more clearly like what is optimization power and how does that lead to reward hacking. Giving a few more examples concretely of like how we found reward hacking in our own environments, and then trying to be a little bit more optimistic and suggesting like an anomaly detection method for reward hacking. So factors. Before I get started, this is sort of one of our traffic environments that we looked at. So basically what's going on here is you have cars merging onto a highway. The RL car is in red. It's controlled by a policy. And then human cars are in gray, and so those are just modeled after like typical human driving behavior. And then the goal, if you imagine yourself as the reward designer in this environment, or like you're the urban planner, is you want the traffic to flow smoothly. But it's actually not really clear, again, a priori, like what is the correct notion of smoothly. So one notion that you might think is like, let's make all the cars go as fast as possible. So that's the proxy reward in this case. Or another notion is like, we want all the cars to reach their destination in as little as time as possible. So that's the true reward. So I think on the surface, it might seem like these two notions of reward are similar and should lead to similar behavior, but we actually show that if you optimize for the proxy, you sort of get this reward hacking behavior. And I guess the overall theme of like all the examples in our work is this idea that stronger optimizers produce this reward hacking behavior. And what they sort of do is they like push against the misspecifications and learn to exploit them. And then you get this reward hacking. And not only is it just a bad behavior, you sort of like get these phase transitions where the qualitative behavior after a certain point in time shifts from sort of what you would expect and want to optimize for versus what actually happens. So what's going on here is, as I mentioned, there's a lot of misspecifications. These just happen typically because the environments that we care about in RL have a lot of stakeholders, different preferences, are more complex. And then so the notion of stronger optimizers that we take is mostly parameter count. So like how big of a function class can the neural network fit? You can also think of this as like training steps, like how much time do I give the model to learn? That should get it closer and closer to the optimal policy for the proxy. And the last two are also explored in our paper, but those are probably more longer term. So like, let's say, imagine you're a self-driving car. If you have higher action space resolution, that'd be like saying I'm allowed to make accelerations to the vehicle more often and more frequently. So I have like more fine-grained control. Lower observation noise would be something like I get better signals from the cameras or just more cameras or less noisy cameras. And you can think of that, sort of imagine that over time as these technological capabilities improve, the model should get better at optimizing whatever objective you give it. So this notion of optimizers becoming stronger is actually pretty natural. And then so what reward hacking is sort of this idea that we have some intended behavior that we want to optimize for, like smooth traffic flow, but then when we over-optimize and push against the misspecified proxy, we get a perversion of what we intended. And actually this happens pretty suddenly, and what we find is this happens pretty suddenly, and so that's why we call this a phase transition. So yeah, again, just as a high level, over-optimizing causes reward function and produces these sudden unintended consequences. So, okay, now I'm going to be a little bit more concrete with how it actually emerges and sort of give a demo of what we found. I'm going to talk about traffic and glucose. So in traffic simulation, what you want is to make the cars flow smoothly. In glucose monitoring, basically what's going on is you have a patient and you're like the RL insulin policy administrator. So you get measurements of their blood sugar levels, and then you're supposed to decide how much insulin to give them. Obviously, this is not actually deployed in the real world, fortunately, but sort of the idea in the long run is if this RL model was good enough, you could actually administer patients insulin through this way. And so this is actually the example I was talking about. You can see the RL cars in red, and the human cars are in blue and white. And so what the smaller model does is it's not as good as optimizing the proxy. So it allows the RL car to merge onto the straightaway. And so if we're trying to maximize the mean velocity, this is bad because all the cars on the straightaway now have to slow down. Whereas if you look at the larger model, what it learns to do is, well, basically it wants to increase the mean velocity, so it just stops the RL car. So now all the cars on the straightaway don't actually need to slow down, and this makes them go faster. But obviously, like now all the cars on the merging lane are stuck, so the mean commute time goes up because they don't actually get to their destination at all. So you can see this is sort of like the notion of how the behavior is hacked. And this actually happens if you look at like the policy model size and you plot this. This happens very suddenly, like after a certain parameter count, that you'll see the larger models start to do this. So this is like an example qualitatively of the phase transition. Okay, so this is to motivate the glucose example. So this table is showing insulin rationing versus annual income. And so if you're not familiar with this notion, insulin rationing is sort of this idea that because insulin is so expensive, patients don't actually administer the prescribed dosage that their doctors give them. So what they'll do is just take less over and then sort of space it out over time. So this saves them money. And you can see actually, if you look at the table, that people with less income tend to do this more frequently than people with higher income. So this table shows two things. A, this is sort of like a well understood phenomenon in the medical literature, which is why it's actually studied, and people are sort of like discussing policy implications for this and how we might address this. We're not making any like moral claims of like what is the right thing to do in this case, but this is just to show that, again, different stakeholders have different preferences. So writing down like one objective, like let's make patients' health better, isn't actually necessarily what people care about. Obviously, other people also care about saving economic costs. Okay, and then so what do we actually find? So if you tell the models to optimize for glycemic risk, which is this notion developed by the medical community, where basically the goal is to like measure how often the blood sugar dips between the safe levels. So the farther away you are from like the safe levels, then the higher glycemic risk you have. And I should note also that the simulator we took was FDA approved. So this is sort of like a well-studied problem in the medical literature, and it's recently been adapted for RL. And so, okay, we tell the models basically to optimize for glycemic risk. They administer insulin at every point in time. And what happens is the larger models get better and better at this. So they're able to like obviously reduce the glycemic risk, as you can see. But by doing so, they actually use more insulin. They're able to do this more effectively, but they also use more insulin. And insulin's pretty expensive. So if you actually keep track of like the cost of the insulin and also factor in like the expected value, risk of going to the hospital, it's actually more expensive to follow the larger model's policy just because they use much more insulin. And so based on the previous table, we might see in some cases that patients may not actually prefer what may seem on the surface like the correct policy. They might not want the larger model's policy just because it's more expensive. And again, I'm not making any claims as to like what the correct ethics behind this is, but this is just to show you that like reward hacking occurs because of these different preferences. Okay, so yeah, misspecifications are basically why it occurs. It's hard to get rid of them. It's a very pernicious problem. I'm sure all of you are familiar with it, working with real-world systems. So, not to end on a totally pessimistic note, can we actually like fix this problem? So, if we're in the online scenario where we have like adaptive models and we can sort of do iterative deployment and get human feedback and sort of keep updating our model, that's good. Hopefully, eventually, we'd expect to like converge over time to a better policy. In our case, we didn't want to focus on this because A, we don't really have that much data, and then B, we wanted to more look at the case where we don't have access to the true reward. Can we do instead just some anomaly detection? And so we allow ourselves this assumption that we have some access to the trusted policy. So the idea here is that some small model has been vetted by the humans as sort of safe and it's probably reasonable. And we're not going to give ourselves any true signal. So the goal is, can we detect if a given policy is actually might have reward hacking? And so the idea here is, let's just measure the distance between the policies. And how we do that is, in the simulator, we deploy the unknown policy, and then at every step in time, we measure what the unknown policy actions distribution is, which is like the red arrow, and what the trusted model would have done at that point, which is the blue arrow. And then we can just like get the KL distance or just some notion of like distribution distances over this trajectory, and then collect all these distances, and then just run stats on them so we can get like the mean, median, and range. And then this will sort of give us some notion of like how far is my trusted policy from my unknown policy. And then the intuition there is, well, the trusted policy is hopefully like safe. And then so if the unknown policy is very far away from the trusted policy, maybe some reward hacking has occurred. Because I think the motivation here is, as you saw, there's like these phase transitions where it's clear that the qualitative behavior shifts. So it should actually be pretty reasonable to detect if reward hacking is occurring. I'm not going to get into the details. You can look at our paper for more, but this is sort of like a table showing the detectors. And you can see that some of the, basically, you can make progress on this, but there's still clearly more work that needs to be done to make this better. And so I'll end on a optimistic note. Reward hacking is tractable because you can do anomaly detection. Thanks to my collaborators for their help on this, and I'll leave this slide up for questions.